All right. So can I get a show of hands as far as how many of you have streaming applications in production right now? Spark streaming in prod? All right, cool. I hope this is helpful to you. Let's start with this. So if you have streaming jobs that are always on 24/7 and these things run for weeks and months on end, I think you have a problem domain like we have, where we have a traffic pattern that is very sinusoidal, right? And so this window here is basically about a 3-day window. And in the middle of the day, it peaks in traffic, and at night, it goes down to a lull. And so our streams never stop. They always run. So I don't really know very many people at all that would have a perfectly straight line, right? And the problem with this is you basically have lulls, and then what happens with your resources if they're idle? They're basically just wasting, and you're just dropping money at that point. So even with this, we know that we can predict these patterns. They're kind of like up and down, and we know when they'll pretty much occur. But we also have unexpected spikes that we cannot predict. And so when we have breaking world news events, these things can cause major spikes in our traffic pattern, and that can be very problematic. Another problem domain I want to kind of talk about is catch-up mode. So you can find yourself in catch-up mode in a lot of different ways. This can result from a lot of different failures, but I kind of categorize catch-up mode as your stream has fallen behind. For whatever reason, it's not processing real time right now. And in order for you to catch up, it means that you have to process greater than 1x, because you have to process your backlog plus real time in order to catch up, right? So if we want to take a look at this graph here real fast, this should grow linearly. And what happened here is we had a network failure. Some of our one Kafka couldn't talk to another. And so we had this drop, and then when we recovered that network, it came up as a cliff, and we're trying to process the backlog to catch up to real time here. All right, so another way you can find yourself in catch-up mode is we do a thing called replay. So replay is when you have to push historical data through the pipeline, and you do that in order to maybe fix a bug, or you want to apply a new feature or transformation. Thank you. A feature or new transformation to historical data retroactively. And that will require you to also process the backlog plus real time. Then you can also get like unforeseen spikes in traffic. All these things can cause problems in your traffic pattern. Right, so these problems aren't new, and you can use traditional methods to cope and deal with these things, right? So typically, what people do is you have a statically sized cluster, and you basically provision that cluster to be able to handle its very peak traffic pattern, and then you give yourself a little bit of wiggle room in case things get a little crazy, right? And that works, it totally works. But the problem is, if you size your cluster up here for the peak, and when you hit a valley, you now have a bunch of wasted resources when you hit the valley, right? And the larger the difference between your peak and your valley, it's going to be the larger the waste. Does that make sense? So I've also seen some people like restart their jobs when they get in catch-up mode, and that's incredibly painful. And with failure like once a week or something, and you say, all right, we're falling behind, we have to catch up. Let's resize the cluster. We'll stop it, reconfigure it to get more servers, and we'll spin it up. And once it catches up, then we'll restart again and spin it down. Like don't do that. That's really, I mean, you may have to do that, but try to avoid that at all costs. So what about back pressure? This is not a very traditional, this is fairly new. Back pressure is kind of this way for an asynchronous consumer to tell its upstream producer, hey, slow down a bit. I can't keep up with your rate. So it will buffer upstream. And this comes from the Reactive Manifesto. It's a brilliant API. It works really well. It's very simple, but yet very powerful. Spark implements back pressure. It's very effective. It does work. With that said, back pressure doesn't solve all of our use cases. So in order to understand why, we need to talk about what happens, right? If you use enough servers and back pressure kicks in, what happens is it says, hey, you're going to overwhelm me, so slow down, please, upstream. And so the result of that is you're going to fall behind real time. Because if you get a traffic spike and back pressure kicks in and it slows down upstream, now you're falling behind a little bit. So you have this lag, you're falling behind, and that may not be an option for you. If you have a stringent SLA to remain real time, then you may not be able to use back pressure in that scenario. However, like, what's worse? Do you want to overwhelm the system and fail, or do you want to kind of fall behind real time? And so generally, yes, it's much better to just back pressure than to completely crash the system. But it's still not the optimal solution. On top of that, once you get caught up after back pressure has stopped signaling upstream, you're going to still have this valley, and in that valley, you now have idle resources again that you're still paying for, right? You can also have very prolonged, sustained spikes. So we had this thing called Brexit happen last summer, if you guys remember that, and that caused, that was a world event. It caused a lot of news to happen, and we got a massive spike in internet traffic for about 10 days. Because people are like, what is Brexit? Why do I care? Why are my local tech stocks failing if something across the pond is happening? What does this even mean? What do you mean, like, why does this affect me? Why is the financial market crashing? Now there are hate crimes increasing in Britain. What does all this mean, right? And so this generated a lot of traffic for us for a very prolonged time. And if back pressure was used for us upstream, our Kafka window is only 5 days. And if my back pressure is kicking in for 10 days, I could actually start dropping off data on that window. And ultimately, your max throughput is going to be limited and capped by the amount of servers that you have. Let's just assume for now that your streaming job is already optimized. It's already parallelized as best as it can be. And sometimes you just simply need more servers to process more data, right? So a solution that we use is called Elastic Spark Streams. So some of the properties of this is it has to auto-scale. And by that, I mean it has to have the ability to add and remove servers to the stream without ever restarting the stream. And it must do this and adjust to the demands of traffic. It has to detect this on its own and be able to do this all on its own without us manually doing anything to it. And a result of that is we can now maximize our resource utilization, which means when we're at our peak, we have our max servers. When we start to drop down and hit our valley, we will start shedding those nodes in the stream. So I do want to say that this isn't just, these aren't just ideas and concepts. Like, this is not vaporware. We've been doing Elastic Streams in production for over a year now. And this is a graph of one of our jobs, just one of them. And so I want to show it's maybe a 3-hour window in the morning. And if this top graph is essentially just a count of the microbatches. It's just how much data this one job is consuming over a 3-hour window. And you can see that it's just slowly increasing. It's a pretty linear pattern. So in the morning, we get more and more data. This middle graph, I'll talk about what processing percentage means later, but this red constant line is at 1.0 or 100%. If you go above that line, it means it's bad. This green line is at 0.75%. If you're below that or just above it, you're still good. So in a perfect world, you want your processing percentage to be right in between these things. And you can see here, you kind of go up, and then you fall back in. You go up, and you fall back down into the proper range. What does that mean? If we kind of look at this vertically, because this is one job, this yellow line down here, these little spikes, is when the stream itself has detected it needs more servers. And so this is a request of more servers here, a request of more here, and a request of more here. This green line, are these little steps, is just a count of how many executors that streaming job has at the moment. So what you see is traffic is increasing in these few hours. We start to fall behind because essentially we just can't keep up. There's too much traffic for that size of the cluster. We detect that here, we request more here, and we get some. And this pattern just continues as traffic is increasing throughout the few hours. Same thing at night. So we're at peak here, and at night we start to scale down as far as traffic goes. And you can see this kind of craziness happening here. But after we drop below this green line, we detect that, and we can start scaling down. Right? And this job here at peak is about 48 servers. Down here, I think it goes down to maybe 14 or so. This is a whole day. So you see it goes up in the morning, it hits remains at peak, and it starts to scale down at night. Same thing with our servers. We go from here, we scale up, and we go down at night. Interesting here, this little blip, right? We see the blip and the blip. What happened there is essentially we had a quick failure, right? This is essentially something happened, it failed, you had to catch up and process extra data. You see the blip there. And then we were in the process of scaling down. It realized the blip, and it basically had to scale back up, and then it continues to scale down in the middle of the night. All right, so implementation-wise, processing percentage it's actually pretty simple to think about. It's just the processing time divided by your microbatch interval. So let's say you're running 5 seconds for your microbatch. And then your processing percentage, which is your processing time, is the total time it took that microbatch to execute. It means the overhead of consuming and producing, as well as whatever transformations and mapping that you're doing, right? So if your microbatch is 5 seconds and that microbatch took 6 seconds, you're at 120%, and that's bad. That means that one microbatch fell behind. If you're less than that, then you're essentially stable for that microbatch, right? Don't ever act on a single data point. When I first started prototyping this, you act on one single data point. Once you go above 100%, you act and ask for more. That's bad, because what it puts the system into a state of thrashing and flapping, because then you're basically just grabbing more servers. Oh, wait, I don't need these. Let me give them back. Oh, wait, I need more. And so you're basically just thrashing the system, and there's always overhead as you ask for more and release some. So you don't want to just don't flap the system. That's a bad thing, because it actually make performance worse. So let's see. Each streaming job has a very unique workload, and by that I mean its processing is different, its microbatch interval is different, its traffic pattern is different, and because of that, you want to create these things as configurable parameters, right? So we have defaults, but you should be able to change these defaults. And so for us, max threshold is 100%. You may want to do 90 because you may want to trigger a scale up before you hit 100%. N needs to be configurable because you want to collect N data points for processing percentage. You don't ever want to act on one, kind of get a sliding window of a trend of those data points, and then act on that trend. You always want to configure the percentage because don't scale up by a constant number. If we're elastic, that means at one moment I could have 10 servers in my job, at another moment I could have 50. And if I scale by 2 every time, it's effective at 10, it's not effective at 50. So you want to scale up and down by a configurable percentage. And probably the 2 calls that you care about to do this thing on top of everything else is Spark context request and then kill executors that will basically nuke it. So this is interesting and all, but how do we know this actually works besides it can scale up and down, right? And the most important thing here is data integrity, right? It's fine if you say this works, I can scale up, I can scale down, I can see that, but if we have data corruption, this becomes completely pointless. Don't do it. It's unacceptable to actually lose data when you scale up and down. So how do we verify that we do this correctly, right? So we have this invariant, and we say that elastic streams are only allowed to affect performance and maximize resource utilization. It cannot in any way affect the data. You cannot lose data, you cannot corrupt the data. So I implemented this random scaler. And you might be thinking, why the hell would you ever want to do that? That sounds silly, right? Turns out there's a pretty good reason why I want to have a random scaler. Because I want to show that if I disregard heuristics at all, I don't even consider any type of heuristics in decision making. I just want to randomly scale up and down as fast as I can. I want the system to flap and thrash. I want to stress out this streaming job as much as I can. And in doing so, I want to show that even in the worst case scenario, when it's just completely stressed out and performance has actually gone worse than doing nothing at all, I want to show that data is still consistent, right? And so what we do is we have this testing suite. I'll say automate all your things. Don't do this manually. Automate everything. We have a command that will basically spin up a Mesos cluster from scratch. It will use one Docker image that's repeatable. That Docker image has the input data set. it's burned, it's not going to change. That's fed in. We have two separate jobs. Those two separate streaming jobs share the same processing logic. The only difference between these two jobs is one has no scaling at all. Very simple, no scaling. The other one does random scaling. And as we watch it perform, you can see that the random scaler is actually much slower than doing nothing at all, because you're thrashing the system, right? And you're really hurting it, but it still eventually will output its data. And then the third thing is another job picks up the output from the other two. And it grabs that output, and it will compare for every record, for every field, for billions of records, are they equivalent? But do remember to do a distinct and a diff, because you may have extra dupes when you're thrashing about, right? If they are equivalent, then we know we're good. If they aren't, then you've violated the invariant, so don't do that. All right, so this is Spark Conference, and I want to focus on Elastic Streams, but I do want to touch on Mesos just real fast, because I feel like if I didn't, then I would leave a hole in the big picture, and I want you to leave here like kind of understanding the entire picture and see how everything kind of fits together. But our Spark jobs essentially are deployed in Mesos. They're Dockerized containers. We launched them via Marathon. If you don't know what Mesos and Marathon is, then I'll leave that up to you to do some research. But so each Spark job can expand and it can contract independently. It doesn't know about its neighbor at all. It just, when it needs more, it asks for more. When it needs to shed them, it just will release them. And so you're probably wondering, well, where does it get all these servers? And what does it do when it releases them? And so it gets them from Mesos, and it will release them back to Mesos. But what happens after that? Because certainly you're thinking, if all the streaming jobs scale up at once, then you're going to run out of servers, right? If you start releasing them all at once, you have this excess supply of servers in Mesos. And so we also have this lightweight app that runs and evaluates the used and unused resources on Mesos itself. And so as the buffer runs out of Mesos, it will actually kick in the automation, and we will gain and add more servers to Mesos. And as it needs to release them, we have an oversupply. It will just basically start shedding those nodes and kill it and give it back to the cloud so we don't pay for it. Conceptually, we kind of talk about these things as balloons and inner balloons. So if you think of each streaming job as an inner balloon, it can expand and contract independently, and then Mesos is the outer balloon. It can also expand and contract as need be to accommodate the inner balloons. Does that make sense? Okay, so metrics, the only reason why I want to even have a slide about metrics is just to kind of for you guys to understand that what is our scale and how many engineers do we have to deal with this, because this has an impact on why we do streams and Elastic Streams. So we have one job that basically does about 5 terabytes a day, and at peak it does over 130,000 seconds, or 130,000 messages per second. That's one job. But the output of that one job a very common pattern for us is we'll ingest from Kafka, and the output goes back into Kafka to other topics based on the event type. So we can fan out and split into a bunch of other topics after we do transformations and cleanse that data. After that, there are a bunch of other streaming jobs that will take in that output and take it in as input to do other things with it based on the actual event type. So the generation of the initial ingest and the total throughput after all the processing is usually greater than 2 times of what our initial ingest is. Our team alone roughly has about 500 to 800 servers at any given moment. That changes constantly because of elasticity. To be fair, some of those servers, probably about 100 of them, are legacy MapReduce jobs that we have yet to convert over into streaming, but we're still working on that. Our team alone spends about $250,000 a month in infrastructure, and that's about $3 million a year. So that's, honestly, if you have like 1 or 2 streaming jobs and your bill is a few $100, $1,000, it's probably not even worth considering something like this, because the impact just isn't that great, right? But for us, at this scale, at this level, with only 8 engineers to support the infrastructure, we write the automation for infrastructure, we provision our own servers, we write the streaming jobs, we don't have a QA test team, we test everything ourselves. So we're on call, this is 8 engineers, we have to do all of this, we're responsible and accountable for this entire stack. At that level, if I didn't have elastic streams, we'd be in serious trouble because we just can't manage that. So the impact for us, right, the operational gains has really freed us from manually babysitting all these jobs. We have over 30 plus streaming jobs running in production. We can focus on the feature development and just know that things will recover after failures and they'll just generally work. The financial impact for us has been really quite big because we spend millions per year. And if I scale down at night, I'm basically shedding those nodes and those servers at night. I'm saving millions per year. And with that, I'm done, and thank you for listening. Do you have any questions?
Please raise your hand if you have questions, and I can run with the mic, get some workout in.
I was curious, what metrics are you paying attention to inside the Spark clusters to know when to like invoke the request executor methods?
Yeah, sure. Good question. So the way we do this is we implement a streaming context lister, right? And so that thing has a bunch of different functions that you can implement to get invoked when that event occurs. And I think the one that we use is onBatch completed. So that onBatch completed gets invoked when the batch completes. And so in that function, you get passed some parameters, and you can evaluate how long it took for that microbatch to complete. And that, for us, is what we basically, it's the processing time. And you know when you start the job what your microbatch interval is. And so if you take that divided by your microbatch interval, you can get the processing percentage of that microbatch. And that, for us, is probably one of the most important metrics because it indicates to you if you've fallen behind or if that microbatch is stable. But to be fair, like I said, like don't act on a single data point because you always have blips here and there that don't necessarily mean the job needs to scale up just yet or necessarily should scale down just yet. So you want to collect a sliding window of those things and then wait until whatever algorithm you want to use, whether it's like an average of those data points or a median or something else, and then act on a trend of those things. And after that, you can basically trigger, if you want to scale up or scale down. Does that answer your question? So look at, there's a streaming listener that you can look at, and from there, you can look at the API and try to figure out what data points you can collect.
I have two questions, really. One, it looks like you're scaling both your Mesos cluster and your Spark jobs separately.
Yep.
And if they are they is that scaling based on the same information?
No, it's not. So I didn't get into this because it's a pretty large scope, right? But in our Mesos cluster, we have a bunch of Spark jobs. But we also have a bunch of web services as well. And so that's a separate thing. They all actually auto-scale. And so we wanted to decouple that. We didn't want one thing to monitor Mesos and Spark and web services because our web services also have different heuristics when they should scale up or down, and that gets pretty deep as well. So to have everything coupled in and try to manage all of it, I think is a little too complex. And so for us, if they're kind of single responsibility for monitoring and triggering scale up and down, it just makes things easier to reason about.
A common pattern when you're ingesting from Kafka into Spark is to align your Kafka partitions with your Spark executors. Are you always forcing yourself to repartition the data?
Yeah, no, that's a really good, insightful question. So typically, in the best case scenario, you have less than or equal to partitions in your Spark as compared to in Kafka. What I mean by that is, let's say it can be problematic if you have maybe only 10 partitions in Kafka, but you have 50 nodes in your streaming. And let's say by 4, that's whatever, 50 times 4, that's how many default partitions you'll have in Spark. And that can be problematic because your consumer is only limited by, or your consumer parallelism is limited by how many partitions you have in Kafka, right? And so what that requires it to do as you're scaling up is then you have to basically repartition or shuffle that data around to split it across all of your servers in order to get the max parallelism you can. And so how we get around that is initially we could try to detect that. And so along with one of your questions, you can also try to detect how many CPUs you have at any given moment, and you can try to adjust to that and say, all right, if I have greater CPU, then I may need to repartition, and we'll do that dynamically. And that works, but our best performance that we've observed is to actually always have greater number of partitions in Kafka than you will have in your larger Spark job. Because if it's greater or equal to, you're going to be much safer that way. That it will require no shuffling of network data. Does that make sense? Okay. Any other questions? Yes.
So I noticed that the method to remove executors takes an ID.
Yeah.
So is there any special logic determining which one gets removed?
Any special logic to find the ID, or?
Well, I guess both. One, to keep track. Are you keeping track of these IDs on your own? And how do you choose which one to remove?
Yeah, we don't keep state around very much. We try to do everything stateless and idempotent as we can. So we don't track it, so to speak, but you can interrogate and query the system after every microbatch when you're collecting those data points to find the executor IDs. I forget it, but it's like storage. It's in a really strange array. I think there's Spark context and storage info somewhere, and then you have to like dig for it and find it, and then you'll find the sequence and the list of IDs for all the executors. And from there, you can try to pick one and then nuke it. And there's some interesting logic that you can do there as far as which one do you pick, and like how do I interrogate the characteristics of a particular node in that job, and how do I pick it. But you can also just say, I'll just nuke this one because they're all the same. Does that answer your question?
So we have time for one more question. All right.
I noticed when you had a blip when you were downtrending,
Yeah.
that the curve was effectively shifted to the right, meaning you have another potential to save money. Can you
Yeah.
speak to how, if in trend of down and blip, if another blip would happen, you don't want to, can you speak to that?
Yeah, so we typically, the percentage at which we scale up and down are separate for up versus down. And we typically are more aggressive on the scale up because we want to never fall behind. And we are a little more conservative on scale down. We could be more aggressive if we wanted to save more money. But for our jobs, we typically want to be a little more conservative on that and say, as long as we do save money and we're being intelligent about it, I don't want to scale down too early and then fall behind again. So, but as long as it's tunable and configurable, then it doesn't really matter. You can change it per job, right?
Right. Thank you, Doug Nguyen. It was great sharing insights on Spark streaming. Thank you.